AB Alabi, Department of Physics. We are on experiment 12, and that is determination of the focal length of the converging lens. We are having an inaccessible convex lens with me here. So we all know that from the principle that now converging lens we usually produce real and inverted image, except when the object is placed very close to the converging lens, or let's say when the object is placed less than the focal length, and that is when you have an erect, virtual and magnified image. Now this experiment is divided into three sections. Number one is the simple method to obtain the focal length. Then the second method is determination of the focal length by displacement method. Then we have the third one, that's determination of focal length by a virtual image method. For the first one, we have the apparatus to be the converging lens, the meter rule, and the wall. We're going to use the wall as our screen. So now we start with the first experiment. Now we take the wall as our screen in this case, and because we are viewing, we have our objects, at infinity. We are considering a distant object, and then we know that objects at infinity will always, be formed. The image will be formed at the principal focus of the converging lens. So, and that will give us the focal length, the approximate focal length of this converging lens. So, now what we do, we place our meter rule against the wall with one hand of the meter rule at the wall, and we move the converging lens on the meter rule to and fro the wall until we now have a sharp image on the wall, sharp image of the window, which is our object now, our distant object. So as we can see, we have it there, and the mark on the tube holding the lens will be measured on the meter rule, as we can see now. So that will give us the approximate focal length of the converging lens. The second method is the displacement method. Now we will need the optical bench, the ray box with cross wire, and the white scale. Now, then we need our inaccessible convex lens. Now, following the procedure, the first thing is we place the ray box and the screen about 7 times the approximate focal length we got in the first method. Now, and that is what I've done now. I have my ray box here, and I have to place the ray box and the screen about 7 times. 7 times. Now, this is about 7 times now. I'm placing these at a point and multiplying the focal length. I have it about 7 times. Now, the next thing is to now place my inaccessible lens in between the ray box and between the ray box and the screen. So I'll make sure it's firm. Okay, so we'll place the we have the inaccessible screen, the convex lens, in between the two of them. So what we do is we move the convex lens towards the screen to obtain a sharp, diminished image of the crosswire. So we have the sharp, diminished image formed on the screen, as you can see now. Now, the reason why we have that is because we all know that if the object is placed in between the focal length and 2f, then we're going to have the real image, but diminished image. Then we note that point. You have to note that point as L1. Now, we know that point as L1. Then the next thing we do, we move the convex lens again away from the screen, and we're going to obtain a sharp magnified image again. We're going to obtain a sharp magnified image of the screen, and that is marked as L2. That's marked as L2. Now, you have to note the difference between L1 and L2. Of course, L1 is greater on the meter rule here than L2. So we have L1 minus L2 as our D. So when you obtain that, now you are going to now begin to decrease, to continue, we are going to decrease the distance between the ray box and the screen in steps of 5 centimeters. So we decrease it in step of 5 centimeters. Now you reduce by 5 centimeters. When you reduce by 5 centimeters, that will give us the new L. Again, we will repeat and place the convex lens in between to get the sharp diminished image again. Then mark as L1, sharp, we get the sharp magnified image again as L2. And that will be repeated to obtain set of 7 values. So that means you obtain a table where you have L1, set of L1, you have set of L2, then you have L1 minus L2, which is your D, which is equal to your D. And then the next thing to do is you obtain L1 squared, then you have your L2 squared, then you have your L1 squared minus L2 squared. So we now record the value of our L, for each step. Then we have the corresponding L1, corresponding L2. Then you have L1 minus L2, which is of course our D. Then you have the square of L1, then square L2. Then you have that S2 square, L1 square minus L2 square. Now you are given an expression. You have an expression that is F equals to L squared minus D squared over 4L. So from here, you have your L squared minus D squared equals to 4LF. So if you look at this, you have y equals to f x plus c. So that we can plot, you now plot the graph of L squared minus D squared against your L. So from where you get your slope to be 4f. Yes. plus 2 for F. Now, when you do that, another thing that is required is we want to know the minimum L, and that is when the distance between the ray box and the screen, where you will not obtain a sharp image again. So if you continue to decrease L, I continue to decrease my L. Now what we do, we decrease the L. Don't forget we are decreasing it 5.5. If you decrease it, at a point, at a particular L, we are not going to, and that is find the minimum separation L for which you will get the sharp image. So at this point, I still have my sharp image. I'll continue to decrease again by 5 centimeters. You check again, you have your image, you have your sharp image. You decrease again by 5 centimeters. You check again until at a point you decrease again by 5 centimeters until at a point now I cannot obtain, so that point will be your L1. So our L minimum, sorry. So we should get our L minimum and record it. Record our observation. So there are other questions there we are expected to answer. Now the third one, determination of the focal length, is the virtual image method. Now we know that when the object is placed between the convex lens and is placed between the convex lens and the focal point, you are going to have a virtual image. Now, but this one cannot be received on the screen. So we lower our screen, we cannot have it on the screen. Then I'll also remove the ray box. So in this case, I'm going to be using I'll be using an image. Okay. So we have now we should take note that to obtain the virtual image, the distance of the object must be less than the approximate focal length I got initially in the first method, and the second method as well. So I will have it here, then I'll put it at a point less than the focal length. Now I will need a search pin to be able to get my image. So what I need to do now, this is like a simple microscope. So now the image is not obtained by tracing the rays, but by extrapolation. Now the object is placed less than the focal length of the converging lens. And now we're going to use the search pin, which is already stationed here, to locate the image obtained. Now, if I look through the convex lens, I'm seeing the image of the object. Now, I'll use the search pin to get the distance. The distance of the image, and that is by parallax method. And that is when the tip of my search pin is at the same point with the image I'm seeing. So the image located with the search pin. With one eye on the image, that we can see through the screen, I mean through the convex lens, and the other eye on the search pin. So the point at which you are having the two tips almost at the same point, there is a coincidence between them. That's the point we are going to take as our focal length. So we adjust it until we get that point, and that will be the focal length obtained by virtual image method. The image distance from the lens is now obtained, and we have the object distance. That's the distance from the object to the lens. And then after doing that, then we repeat again for another position of the object. Of course, it's still going to be less than the focal point that we got, the focal length that we got in the first method. So we'll change the position of the object and then repeat again to get the corresponding image distance, where you're going to have coincidence between the image, the object and the search pin. So now when we do that, then we will now find the average. So we obtain the average of the image distance. Then we have the average of the object distance. So now going back to obtain the focal length, because the focal length is a virtual image, so it's going to be negative, and that's why we have the negative value here. So when we do that from here, we can get the focal length of the converging image. Okay, so after obtaining the focal length for the virtual image method, now we compare the value we got from the first method, from the simple method with the displacement method. Then we compare with the value we got from the virtual image method and see if they actually the same, and that's will confirm the focal length of the lens given to us. Thank you.